p of x and q of x, where p is a naught plus a1x plus a2x squared plus up to a m xm, and q is b naught plus b1x plus bn xn. I'm going to tell you something funny, which is that if the polynomials agree on any tiny interval, AB, then they must be identical. If they, so suppose that, sorry, I'm running out of ink here. So what I'm saying is that, and this is, you don't really need to know this, but it's sort of cool, that if there's some tiny interval, and it turns out that the first polynomial does something in that interval, and the second polynomial does exactly the same thing in that interval, then the polynomials are forced to agree everywhere on the real line. They are the same. They're the same polynomials. Okay, that's kind of interesting, but we don't need it. Let me say something say something a lot weaker. If they agree on if they agree, then they must be the same degree and have the same coefficients. This is something called I guess you could call this an identity thing. Identity theorem. Okay. You can't have polynomials with different degree that agree with each other, or different coefficients that agree with each other. Okay, so maybe this seems obvious to you, but let me just talk about it a little bit more. So if your two polynomials agree with each other, then for example, so why must they be the same? Why must they be the same? Well, if we consider p at 0, right? Consider p at 0, right? What's p at 0? If I put in 0 to the polynomial p, then what comes out? Is somebody saying it? Maybe this is too abstract, but let me say it like this. Suppose I have this polynomial, 2 plus x squared, right? What happens when you evaluate it at 0? What do you get? You get the 2, right? You get the constant term, right? So if you look, so think if we have these two polynomials and they agree everywhere, then the fact that they agree at 0 means that they must have the same constant term, right? So right, you have these two polynomials. Suppose they agree everywhere, okay? Then P naught and Q naught, P of 0 and Q of 0 are the same thing, and that tells you that A naught equals B naught, right? That tells you that A naught equals B naught. Okay. Going on in this vein, if we consider P prime at 0 and Q prime at 0, right? What do you get when you take P prime and evaluate it at 0? What do you pick up then? If I take the derivative of this polynomial and then evaluate it at 0, I'm going to pick up A1, right? I'll pick up A1 and I pick up B1 here, right? So since the behavior is the same, I know that the derivative at 0 is going to be the same. So that tells me that A1 and B1 have to be the same, right? And you keep on going like this. You take the second derivative, right? The second derivative, P double prime 0, what's that? Well, that was going to give me 2A2, right? So I know that 2A2 equals 2B2. So A2 and B2 are the same, and so on and so forth, right? So then you get that all the coefficients are the same, and that tells you that the degree must be the same also. Okay. So, okay. So this is just saying that if two polynomials agree on the whole line, in fact, what this is saying is that if they agree near the origin, then they have to have the same degree and they have to have the same coefficients. Second thing, factorization, unique factorization of polynomials. Okay, so what this says is that given any polynomial, p of x, again being a naught plus a1x plus a sub n x to the n, it has a unique factorization into what we call irreducible elements. There's a unique factorization into irreducible elements where those elements are linear terms, that is, things that look like x minus r, and quadratic terms, irreducible quadratic terms. X squared plus ax plus b, where a squared minus 4b is less than 0. So maybe you've seen this sort of thing before, right? You can take a polynomial and then you can factor it into these smaller factors, right? So right, like I don't know, something simple. So like, if I have x squared minus 1, I can factor it into x plus 1, x minus 1. Right. That's all we're saying. That any polynomial, you can break it down into these simpler parts. Okay. Sometimes the parts could be quadratic, right? Sometimes the parts could be quadratic. You can't factor this any further in the real numbers, right? If you're in the complex numbers, this would break down into x minus I, x plus I, right? But in the real numbers, this is an irreducible quadratic. Okay, so anyway, this is a theorem called the fundamental theorem of algebra. Fundamental theorem of algebra. That any polynomial can be factored into linear parts and irreducible quadratic parts. Tom, can I trouble you to try to find another marker? This one is running out. I really need it. So, I don't think there's any more here. So. Okay, so okay, so here's the main thing we're going to use. The main theorem that will be useful to us. Okay, it's this: every proper rational function can be uniquely expressed as a sum of what are called partial fractions. Okay, and these partial fractions are functions of the form a over x minus alpha to the k, and things like bx plus c over x squared plus beta x plus gamma to the k, where again b squared minus 4 gamma is less than 0, right? Where this quadratic is an irreducible quadratic. Okay. So every proper rational function can be expressed as these simple guys. Okay. So that'll be the game, right? Somebody says integrate this rational function. And then you say, okay, well, I'm going to take that rational function and break it into these simple guys, and I know how to integrate these simple guys, right? You can integrate this sort of thing easily. You can integrate this sort of thing using trigonometric substitutions, or sometimes the logarithm. Let me give some examples to show how this happens. So 2x. It turns out, for example, 2x squared plus 3 over x minus 1 squared actually equals 3 over x plus negative 1 over x minus 1 plus 5 over x minus 1 squared. So this rational function is expressed in its partial fraction decomposition. And we'll show you how to get the partial fraction decomposition in a second. But I'm just gonna put down some examples first. So another one, x squared plus 5x plus 2 over x plus 1, x squared plus 1. Its partial fraction decomposition looks like this: 1 over x plus 1 plus 2x plus 3 over x squared plus 1. So again, you see, these guys are partial fractions, and it's a partial fraction decomposition of this guy. Maybe you're noticing some facts about it, right? That the partial fractions that show up are related to the denominator, right? The factors in the denominators here occur in the denominator here. Okay. Third example, 3x to the fourth plus x cubed plus 20x squared plus 3x plus 31 over x plus 1 times x squared plus 4 quantity squared equals 2 over x plus 1 plus x over x squared plus 4 plus negative 1 over x squared plus 4 quantity squared. Okay. Again, you have this partial fraction decomposition. Okay. So, this is good, right? Because if somebody tells you to integrate this, that's hard. But if somebody tells you to integrate this, this is easy, right? This you know, this you can do now, right? Given what we just did in the first half of the class. Okay. Okay. So, how do you get the decomposition, right? How do you? That's the question, right? How do you get the decomposition? How to get the partial fraction decomposition. Okay. So here's the thing. So somebody gives you, given a proper rational function p over q, a proper rational function, first thing you do is to factor q. It's just becoming more and more invisible. Factor q. Okay, so factor the denominator. That's the first thing you're going to do. If the factorization contains, say, x minus alpha to the k, then the decomposition contains things like great, thank you. Save this. Okay, sorry about that. Okay, then the decomposition can contain terms of the form a1 over x minus alpha, a2 over x minus alpha squared, blah, 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 ak over x minus alpha to the k. So okay, so if you see, so for example, here we have this x minus 1 squared, right? X minus 1 squared, and lo and behold, we have things that have some number over x minus 1 and some number over x minus 1 squared. Okay. If it had a cubed here, then you could all go up to 1 over x minus 1 cubed. Okay. Similarly, right, if the factorization contains the quadratic guys, x squared plus beta x plus gamma to the k, then you could have things that look like b1x plus c over x squared plus beta x plus gamma, b2 x plus c2 over x squared plus beta x plus gamma squared, up to the kth power, bkx plus ck over x squared plus bx plus gamma to the k. Okay, so right, here's the example, right? This guy in its denominator has a quadratic squared, and so you have these things, right? You have you know, a linear term over the quadratic, you have a linear term over quadratic squared. Okay, so what you do, right, this once you factor the denominator, then you know what the form looks like. You don't know exactly what the coefficients are, but you know what it looks like. And then you play some game to figure out the coefficients. Okay, so the fourth thing is you figure out what A1, etc. all these coefficients. Figure out the coefficients. Figure out the coefficients. So we'll do some examples of that. Okay, so examples. Okay, so here's one. 1 over x plus 2, x minus 2. Simple example. You have linear terms on the bottom, so you know that it's got to look like a over x plus 2, and some other number over x minus 2. Okay. And then if you want, you can call them a1 and a2. I used a's over here, but it doesn't matter what you call them. It's just some number over x plus 2 and some other number over x minus 2. Okay. So how do you figure out? You figure out A and B. One way is to say, well, look, so here's method 1. You multiply through and you say 1 is equal to a x minus 2 plus b x plus 2. Right? Just multiply, clear out the denominator. Multiply through by x plus 2, x minus 2. Right? You get this, right? And so you see that a plus b x minus 2a plus 2b equals 1. Okay. At this point, you pull out the identity theorem and you say, I have a polynomial and I have another polynomial. Right? I have these two polynomials that are equal to each other, So they must have the same coefficients. Right? The two sides, the two polynomials must have the same coefficients. Right? So what does that tell us? That a plus b is 0, right? Because over on this side I have 0x plus 1, right? So the coefficient of x is a plus b, the coefficient of x is 0. A plus b equals 0. Similarly, I see that negative 2a plus 2b is equal to 1. Right? If you work that out, that gives you that a must be a fourth and b must be negative a fourth. Okay, so that gives you your expansion, that gives you your decomposition, right? This is going to be 1/4 over x plus 2 plus negative a fourth over x minus 2. Okay, method two, evaluation at cleverly chosen points. Okay, so right, you have this 1 is equal to a of x minus 2 plus b of x plus 2, right? So maybe what you say is that, okay, at x equals 2, what you see is that 1 equals b times 4. So that tells me that b is 4. Right? Similarly, at x equals minus 2, you see that 1 equals a times negative 4. Right? So a must be negative 4. Okay, so you choose, you intelligently choose places to evaluate your polynomial so that you can get information about the a and the b. Okay, and those are basically the two methods that people use, and you can combine them together, right? So, maybe you could come to here and say, I know that a plus b equals 0, and you evaluate, and you say, I know that b equals a fourth, and so a must be negative a fourth. Right? So you can combine the information however you feel like. I should say that although this might seem like a very esoteric technique, it does actually show up when you try to do differential equations or complex integrals. So it's when you're doing complex variables, strangely, this sort of thing will show up also. Well, not strangely, it will show up again. Okay, so you might think, why do we need to know this technique? This technique actually will show up later. Unlike, so this is a useful one, at least if you're going on in mathematics. Another example. Let's do some examples. So 2x squared plus 3 over x minus 1 quantity squared. Okay. So I'd like you to take 10 seconds and write down what the decomposition should look like. What kind of things can you have over here? What's the form of the partial fraction decomposition? Okay, 10 seconds is up. What does it look like? You look at the base and you say, well, I have linear terms and I have linear terms. I have powers of linear terms. So what can I have over here? Jump over.
A over x.
Yep.
B over x minus
What do you want me to put here?
1. X minus 1.
Okay, x minus 1.
And C over x minus 1 squared.
Exactly. Good. Great. Okay. Is everyone okay with the rule? Right. Okay. And then question? Anybody? Yeah.
Why is A over x minus 1?
Yeah, so that's the rule, right? If I'm sorry?
Just x minus 1.
Just x minus 1?
Yeah.
Well, I mean, so you oh, just x minus 1 here?
Yeah.
But that you already have that sort of term, right? You don't need to, right? So remember the rule. The rule is just that, you know, if you have some power of a linear term, then you can have up to that power, right? Up to that power. Okay. Okay. So right. So then you multiply through, right? 2x squared plus 3 is equal to a x minus 1 squared plus b x minus 1 plus c x plus cx. Right. Oh, yeah.
I get lost when you write down the b divided x minus 1. I don't know why you didn't have it. Why don't you just have a over x plus a over x minus 1?
I have to say that that's just the rule. So over here we have this rule that if you have something like if you have any term like x minus a to the k in the denominator, and we didn't really give an explanation of this, so you're right to say that, you know, you don't know why this happens. This is you know, a pure, just like I'm telling you that this is how it happens. Okay. I'm sorry. It'd be nice if I actually explained it, but I'm not going to. Okay. If you have this in the denominator, then you can have things like occur in the partial fraction decomposition. Okay, so over here we have an x minus 1 squared, and so we could have an x minus 1, and we can have an x minus 1 squared term. Okay, and then the other rule was that, right, if you have x squared plus beta x plus gamma to the k in the denominator, then you can have things like b1 x plus c1 over x squared plus beta x plus gamma to the 1, b2x plus c2 over x squared plus beta x plus gamma to the 2, etc. bk x plus c sub k over x squared plus beta x plus gamma to the k. Okay, so these are things that could occur. Okay, so this is, I'm afraid that this is just a rule that you remember. Okay, so over here, right, you just say, oh look, there's a linear term squared, so I know that my partial fractions, the kind of partial fractions that could occur are the things that, you know, something over x minus 1 or something over x minus 1 squared. Right? If this thing were cubed, then I would know that there could be things like this also. Okay. It's just a rule.
Like over here,
Yeah.
you just have a on top, but like for the second one, you have a b times x.
Yeah. So this is for if linear guys occur in the denominator, then you have only constants on top. If you have quadratic guys, if you have powers of quadratics in the denominator, then you have linear term over quadratics. You have things that look like this. Okay. We haven't done any of this sort of example. I'm going to do one after we finish this one. Okay, so just hold on, and we'll finish this one, and then we'll do another example.
If I change that x into x plus 1 squared, well, that was
X plus 1 squared?
no, not this one, but like change the single x into x plus 1.
Here?
No, like the original.
This one?
Yeah.
Oh, yeah. Okay.
If I change that into x plus 1,
Yeah.
constant square.
Okay, so if I had an x plus 1 quantity squared here, then I wouldn't have anything like this, right? Rather, I would have things that look like this, and I could also have things that look like this. Okay, right. So depending on the power of the term, you go all the way up to that power. Okay, so here we have just the first power of x. So this is the most complicated thing that'll happen. Okay, so let's go on, right? And what do you see? If you compare coefficients, right, the x squared coefficient here, right, the x squared coefficient here is 2. What's the x squared coefficient over here? A plus b, right? A plus b, right? If you work it out, you look at the x squared coefficients, right? If you look at the coefficient of x, what you get is that 0 is going to be negative 2a minus b plus c. And if you look at the constant term, right? The constant term, well, you've got a 3 here, and over here you have a, and you have